one end of a stretched string is attached to a wall. Then the other end of the string vibrates with frequency F1. The standing wave is set up along the string. The tension in the string is now tripled while maintaining the same number of loops in the string. If the new frequency of vibration of the string is F2, the ratio of F2 over F1 is, they have given there is the same number of loops. It means wavelength is constant. Then we can use V equals F lambda. Velocity of a wave in a string, square root of tension over mass per unit length, or linear density. We can write it, we can define it as linear density, simple F. F lambda. Now, for both situations, lambda constant and tension constant. There is the same tension for both situations. Sorry, lambda constant and simple N constant. Tension is not constant. Then we can get frequency directly proportional to square root of tension. For the first situation, I will consider tension as T. Frequency is given as F1. For the second situation, frequency F2, now tension is tripled. It means 3T. There are two equations we can divide. F2 divided by F1 equals, T is cancelling, root 3. Then answer is 3. The frequency of a tuning fork is 256 Hz. When it sounded with the sonometer wire, 3 beats per second were heard. When the tension of the wire is reduced, again 3 beats per second were heard. The frequency of the sonometer wire after reducing the tension is, we know that beats frequency is difference of frequencies. Now they have given frequency of tuning fork 256 Hz, and for the first situation beats frequency 3. It means frequency of vibrating wire should be greater than 3 or less than 3 when comparing with 256. It means frequency of wire should be 259 or 256. Both values are not correct, but there is only one correct value for the question. Then they have given when the tension of the wire reduced, again 3 beats per second were heard. We know that when decreasing tension, frequency should be decreased. Therefore, if we are considering this value, then decreasing frequency, the gap of frequencies between wire and tuning fork should be greater than previous value. But if this value is the tension in the wire, then decreasing frequency, we can obtain 253. Then again we can get difference as 3. Therefore, frequency corresponding, initial frequency corresponding to the sonometer wire should be this value, 259. They have asked frequency of sonometer wire after reducing tension. Therefore, initial frequency should be 259. They have asked after value. After value should be this one. When decreasing tension, frequency is decreasing up to 253. Then 253 is the answer. Second one is correct answer for the frequencies of fundamental and first overtone of stretch string fixed at both ends are F1 and F2 respectively. The ratio F1 over F2. There is only one loop for the fundamental frequency and there are two loops for the first overtone. It means for the first situation, half of wavelength should be equal to length of the wire. For the second situation, half of wavelength into 2 should be equal to the length of the wire. I will consider wavelength for the second situation lambda dash. Then we can observe that lambda over 2 equals L. Then for the first situation lambda equals 2L. For the second situation lambda dash over 2 times 2 equals L. There is the same length. Then lambda dash equals L. Then comparing wavelength, we know that wavelength corresponding to the fundamental is 2 times wavelength corresponding to the first overtone. Then we can use V equals S lambda for both situations. First situation, V equals F1 into lambda is 2L, fundamental. For the second situation, V is same, frequency F2, now wavelength L. We can divide two equations and we have to subject F1 over F2. Then we can get F1 over F2 equals half, it means 0.5. Then answer is 1. A string is stretched between two fixed supports. It is observed to have two consecutive resonance frequencies at 300 Hz and 400 Hz. The lowest resonance frequency of string is. We know that for resonance status in a string, we can observe fundamental F0, first overtone 2F0, second overtone 3F0, 4F0, like this. Then difference between two consecutive overtones should be equals to F0. Now they have given two consecutive frequencies 300 and 400. Difference is 100. Difference is F0. It is equal to 100. Therefore, fundamental frequency of the wire should be 100 Hz. It is the minimum frequency we can observe for the wire. Then answer is 2. Two strings A and B having equal lengths L and equal cross-sectional areas but different densities D and DB are connected together and the composite string is stretched across fixed walls as shown in the figure. Two pulses simultaneously sent along A and B from two ends X and Y at t equals 0 are found to pass through the center O of the string at time TA and TB. If dA equals 4 dB, then we have to get relationship between TA and TB. To both pulses, there is the same distance to pass this midpoint. We can use SC equals UT for the pulse, for two pulses. Then we know that time is distance constant. Time is inversely proportional to velocity of pulse. U means velocity of pulse. We can write it tension over linear density square root. Tension is constant. Linear density means mass over length. And we can write mass volume into density. Volume is cross-sectional area into length into density D divided by this length of the wire. Then we can get linear density directly proportional to density of wire. Then we can get time inversely proportional to velocity of pulse in a string. Velocity of pulse equal to the velocity of wave in a string. It is tension over linear density. Linear density directly proportional to density of the wire. Then we can write time inversely proportional to square root of density of wire. For the first situation, we can get time TA directly proportional to 1 over dA. For the second situation, time TB inversely proportional to square root of dB. Now we can divide both the equations. TA divided by TB equals dB divided by dA root. But there is a relationship between dA and dB. They have given dA equals 4 dB. Then we can substitute 4 dB for the dA value. TA divided by TB equals dB divided by 4 dB root. We can cancel out dB. Then we can subject dB equals square root of 4 to 2 times TA. TB equals 2 times TA. Then answer should be 4. One end of string of mass per unit length, simple M is connected to a prong of tuning fork, and other end is connected to a mass capital M after passing over frictionless pulley as shown in the figure. When the tuning fork is vibrated, the string vibrates, forming a standing wave as shown. The frequency of the tuning fork is. It is a Mayday string. There are two types of vibrations in a Mayday string. We have to understand if the tuning fork is connected like this, like in given figure. Frequency of wave generated in wire is equal to the frequency of tuning fork. For the second type, if we are connecting tuning fork like this, we can draw any resonance state, fundamental, first overtone, second overtone, or third overtone. Now, frequency of the wire is half of tuning fork. You have to remember it. And for both situations, we can observe transverse waves in the string. We can't vibrate the string longitude type for this method. If you are using tuning fork to vibrate, always resonance type is transverse. Now they have given this situation. We have to get the frequency of the tuning fork. There are 4 loops of the wire. It means lambda over 2 times 4 should be equal to the length of the wire. It is given as capital L. So we can write lambda over 2 times 4 equals capital L. Lambda equals L over 2. Now we can use V equals S lambda for the wave in the string. V is the velocity of wave, velocity of transverse wave tension over linear density, equals to F is frequency, frequency of wire equal to frequency of tuning fork for this situation. Lambda is L over 2. Then we have subject F 2 over L times square root of tension over mg. Tension is equal to the weight of this part, mg. Then mg over simple m. Answer is 1. A violin string of length 0.5 meters is tuned to fundamental frequency of 440 Hz. To obtain fundamental frequency 550 from the string, at what distance finger B is from the sound box end. We can use V equals S lambda. Lambda is 2 times resonance length for the fundamental frequency. We know that for the fundamental frequency there is only one loop. Lambda over 2 equals L, then lambda is 2L. We can use for the first situation, V is constant, frequency 440, 2 times length of the wire is 0.5. It is first equation. For the second situation, V is same as following situation. V is depending on tension and linear density of wire. Those are constant. Fundamental frequency should be 550. 2 times we have to find the resonance length. I will consider it as L. Second equation. Now there are 2 equations. Left hand sides are same. Then we can equal right hand side. 440 into 2 times 0.5 equals 550 into 2L. Then we can find L value. 2 times 0.51. We can cancel out 440 and 550. 4 and 5. Then we can subject L. 4 divided by 5 into 2, 10. 0.4 meters. Then answer is 4. When the tension of a guitar string is doubled without changing length of the frequency, the frequency of the tone wheel, we can use V equals S lambda. Velocity of wave in string, tension over linear density, root S lambda. Now tension is doubled, therefore frequency should be root 2 times. Then increase by factor of root 2. Answer is 3. Both knots and antinodes of a standing wave of period T have 0 vertical displacement at time T equals time T naught. This will happen at next time. We know that when vibrating a string, I will consider in fundamental situation. When time is t0, it is like if it is like this. After 1/4 of period, it means when time t0 plus t over 4, it should be like this. This end is not, this end is, this midpoint is antinode. Again, node and antinode come to the same level after half of period. When time is t0 plus 3t over 4, it is like this. And when completing full period, it should be like this. We have given this situation. We have to get next situation. Time at next situation is t0 plus t over 2. Then answer is 2. When a guitar string sounds together with the tuning fork frequency 191 at the room temperature, 5 beats per second are heard. It means difference between frequency of tuning fork and wire should be 5. When the tuning fork is heated up to a certain temperature, the beats frequency heard increased to 8 per second. Frequency of notes produced by guitar string at the room temperature is. We can observe 5 beats for the first situation. Frequency of tuning fork is 191, therefore frequency of wire should be 196 or 186. Difference is 5. When increasing temperature, length of the tuning fork is increasing. We know that we can observe a low frequency for the tuning fork with high length. Therefore, when length is increasing, frequency of tuning fork is decreasing. Therefore, this value is decreasing when increasing the temperature of the tuning fork. When decreasing this value, gap between two frequencies should be 8. It is greater than initial situation. Therefore, initial frequency of the wire should be 196 Hz. Then answer is 4.